Yes, hello students. Today I will explain you how to do an experiment on LED, that is light emitting diode. So I will show you the demonstration and we also take some readings to draw a graph. A light emitting diode is a luminescent device which gives light when it is under forward bias. An LED works on the principle of injection carrier luminescence or simply electroluminescence. Electroluminescence is the process in which a device emits light by the application of applied voltage. There are several luminescence processes like bioluminescence, chemiluminescence, sonoluminescence, and one such luminescence is electroluminescence. We are using here the principle of electroluminescence. That means we apply some voltage for a PN junction diode, and that diode emits light from its junction. Ordinary diodes, they emit heat across the junction when they are in biased condition. But some materials like GaAs, gallium arsenide, and other semiconducting materials, they will give light instead of heat when they are under forward bias. Therefore, to make an LED, we require special semiconducting materials. Silicon and germanium are not suitable for LED applications. They produce heat instead of light, but an LED gives light when it is in forward bias. So, either you can use a direct band gap semiconductor or an indirect band gap semiconductor to make an optoelectronic device. But the efficiency of an LED is good if you are using a direct band gap semiconductor like GaAs, gallium arsenide. In this experiment, we are doing with a GaAs diode and it is operated in forward bias. So LED materials is one part selection for good efficiency, and the structure of LED is another important aspect to get the confinement of emission of light. Therefore, LEDs are available as homojunction LEDs, heterojunction LEDs, and also as different structures. That means you have to know how to design an LED for efficient ejection of photons, because an LED material or LED itself converts the applied voltage into optical energy. So an optoelectronic device, if I say, involves the electronic interaction when an external energy is given either in the form of voltage or in the form of optical energy. Thereby, optoelectronic devices can be broadly classified into two types. In first type, if you apply some input voltage, they will give rise to output in the form of optical energy or light. For example, LED and lasers come under this category. We apply some voltage to the device like PN junction diode, and the output will be in the form of optical energy. In some cases, we will give optical energy and we get electrical energy. That means the optical incident energy is converted into electrical energy. And the examples for this category includes solar cell and photodiodes. So optoelectronic devices includes many devices like LED, laser, photodiode, pin diode, solar cell, etc. But most of these devices works on the principle of electron hole recombination or electron hole generation. So electron hole pairs are generated or electron hole pairs are recombined. LED uses a recombination of an electron and a hole. We know that hole is a lack of electron in a covalent bond. To form a covalent bond, we need to bring the electron or say valence electrons of different atoms nearby and a covalent bond is formed. If you supply energy, the covalent bond gets break. Once it is broken, we have electron and hole as charge carriers. But when an electron from in the solid falls into a hole, then a covalent bond is regained. Thereby, when the amount of energy supplied to break a covalent bond is also same as that of energy required to form a covalent bond. Therefore, when an electron recombines with a hole, it loses energy and gives that energy in the form of heat or in the form of optical energy. If that is giving in the form of optical energy, you can use that material to make an optoelectronic device such as an LED or laser. LEDs and lasers are fundamental sources used in optical fiber communication. But there is a difference between LED and laser. Laser light is monochromatic, highly energetic and more directional, and it is also monochromatic. But LED is not that monochromatic. We have some line width and it is also not high intense as that of laser light. So LEDs are cheaper compared to laser sources. Maintenance of laser sources is of difficult nature, whereas LEDs are easy to maintain and also easy to use them without much external circuitry. That means the lasers require some cooling system sometimes, but LED does not require any other additional circuits or additional attachments for its operation. LED is very cheap and therefore it is also widely used in optical communication system as a source. Now I will show you the demonstration of an LED and we'll draw forward and reverse characteristics of an LED. Remember that LED, light emitting diode, is a PN junction diode operated in forward bias. But the difference between ordinary diode and LED is that LED gives off light, whereas ordinary diode gives heat when it is biased. And we use mostly direct band gap semiconductors with large band gap for LEDs. Whereas in ordinary PN junction diodes, silicon, germanium are widely used. In LEDs, GaAs, InP, GaAsP, GaAsP are the semiconducting materials used to manufacture LEDs. Yeah, dear students, this is the experimental board to do various diode characteristics on it. If you see this board, you can do here the experiment for silicon diode in forward bias. This is the silicon diode. We have already done this experiment. If you go here, we have another diode, okay, which is of course in reverse bias. You can do it. This is light emitting diode in forward bias. This is light emitting diode characteristics can be studied by using in reverse bias. And this is the GNR diode in forward bias. This is GNR diode in reverse bias. Therefore, you can do on the same board the characteristics of ordinary junction diode in forward bias and reverse bias, GNR diode in forward bias and reverse bias, LED in forward bias and reverse bias. See, this is is fitted with a digital ammeter where you can choose your own range. Either you can keep it in 2 microamperes or you can go up to 200 milliamperes. That means you can select the appropriate range of the ammeter and you can measure various readings. And coming to the other side of this, here we have another meter, DC voltmeter. This is also digital meter and you have a lot of selection here. You can keep this to measure in 200 millivolts or 2 volts range or 20 volts, or you can keep 200 volts. So for this experiment I can keep either this in 2 volts or 20 volts depending on the values what we are getting. This is 200 volts. So this is 20 volts. I am keeping in 20 volts. Now see the circuit. They have given the connections at different test points. We have here TP3, test point 3. And see, it started from test point TP2, that is test point 2. This is test point 1, where they have internally connected a voltage source of 12 volts. And there is a potentiometer here where you can change this to change the voltage applied in the forward bias. If you come here, you can see a common point TP10 and we have TP11, test point 10 and test point 11. So you need to connect now voltmeter and ammeter in the circuit. So I have switched off the power to the board. First I'll make a connection to this and later we'll switch on the power, then we'll take a set of readings. Look now, I am connecting an ammeter between TP6 and TP10. First I take a TP6 point, test point 6, connect it to the ammeter here. I am connecting here ammeter. Now connect here TP10 and connect to ammeter another terminal. Okay, 2 terminals I have connected between TP6 and TP10. Now you need to connect TP3, that is a test point 3. I have taken test point 3 and connect this to voltmeter. I am connecting to voltmeter. Then I am taking TP11 and connect it to the second terminal of the voltmeter. Understood how I have connected it? The circuit is ready. I switched on the power and this is the cable to the board which I have connected to external supply. So AC is coming to the board from this and the AC will be given to this experimental board which will be converted to DC. We have DC source here plus 12 volts. Now to change the current through the forward biased LED, I have to change this knob. But you see that whenever there is a certain amount of current that is passing through LED, then only it will emit light. So initially, if the current that is passed through the LED is less than the minimum requirement, then it will not emit light. So we have to initially slowly and gradually increase the voltage. At certain point the current through the LED increases to cut-in level. More than that, then light comes out of it. If you see this one, there is no light coming out of this LED. You have to closely observe when the light is started coming from it. And as I am increasing the voltage, after certain point the intensity of the light increases, and you can observe while doing the experiment. And I am showing the tabular forms here. These are the tabular forms for forward bias and reverse bias. So LED forward bias, we are starting from 0 voltage. This is okay. This is 0 voltage I am starting with. Current is also 0. Look at the meters. So the meters, both of them, they are showing 0. Now I increase this voltage simply maybe around 0.05. Okay, I am adjusting it. Now it is showing 0.07, but the current is 0. See, there is no light coming out from the LED also. So therefore, I write the second reading as 0.07 and current value as 0. Okay. So now I take the next reading. I am adjusting this to 0.1. Okay. So 0.1, and there is no current still, and no light is also coming from the forward biased LED. So I note down this reading as 0.1 and current as 0. Now I will increase this to 1.5. I am increasing 0.2. I am increasing to 0.2 directly. See this. Now it is 0.2, but current is 0 and there is no light coming out of this. So I write 0.20. This is a 0. Now I increase the value to 0.25. I will see that there is no current still, no light coming from the LED, and the milliammeter is also showing 0. So while doing the experiment, I kept the voltmeter in the range of 20 volts, and we kept the ammeter in the range of 2 milliamperes. Okay, so I note down 0.25 and corresponding reading as 0. Now I increase this to 0.3. I note down the values of current, and also I'll see whether I am getting any light out of the LED or not. Still there is no light coming out of it. Therefore I write the value as shown by the meter as 0.3 in voltmeter and 0 in the current. Now I increase this to 0.35. Okay, it is showing 0.36, 0.35 it is showing, and I note down this as 0. And now I increase this to 0.4. 0.4, look at the current reading. Okay, it is still 0. I wrote 0.41 and current is 0, and no light is started coming from the LED. So I increased to 0.5. So it is showing the value of 0.5. Still the current is 0. I note down current 0. Now I increase it to 0.6 and I'll write 0.6 and 0. Now I'll go to 0.7. So I note down 0.7, also 0. Then I'll go for 0.8. Okay. Still it is showing 0 only. So I make it note of 0.80, 0.8, and I write the values like this. So if I increase this to further value of 0.9, see the value is 0.9 and current is still 0. I make a note of this and I put 0. Then I increase to 1. Still there is no current and no light coming out of it. So 1 also I keep at 0. Then I'll go to 1.25. I'm increasing. Okay, see this. 1.25 I'm going. So it is 25. There is no current still. So 1.25 0. And I go for 1.5. I'm increasing to 1.5. And the current is now started. See, it is 0.009 milliamperes, but still light has not started. Okay, so light is light. So I light 1.50 and current is 0.009 milliamperes. Okay, so now I'm going again to 2 volts. See now, 1.6 itself current light started from the 1. Light is just started. See, you can see a little spot, very small spot of light coming out of it. Current is increased. So 1.58 I have and 0.044 amperes current, milliamperes current. Now I am increasing this to see the light. See, the light is coming now from LED. Okay, LED started giving light. So I am now going to 1.65. So if it is 1.65, current has increased, and you can see the light coming from the, okay, see that light is coming. Light is coming from the LED. Okay, so the value is 1.65 and the value of current is 0.113 milliamperes. Now I increase this one to around, see this light intensity is increased. I am going to almost 2. I am going nearby. Now it is 1.75. Okay, I'll take 1.75. See, the light intensity is now increased. The current is also increased as 0.439. So if I increase further, it is going as 1.8. Okay, we'll take 1. Yeah, 1.8 or okay, then I note down current as 0.645 milliamperes. I further increase this one and see now, okay, now I increasing, but intensity of light is increased from the LED. See how much. So I am going to 1.85 and the current is 0.916 milliamperes. Okay, 14. Okay, now the light is much intense. Now I am increasing this further. Okay, so 1.9 and the current is 1.281 milliamperes. So now I stop here. Maximum I am going as 2. Okay, so it is 2. So 2 volts, but current range as more than 2 milliamperes. Therefore, I am going to 200 milliamperes range. If I change it, it will be 2.4. I stop here taking the readings, and this is the forward bias. You have seen during the experiment that as the forward bias voltage applied is increasing, at certain value of current, the diode started giving the light from its junction. So the light will be emitted from the junction of the PN junction diode, and once the applied voltage is supplied sufficient and minimum required current, the light started coming out from the junction. So afterwards, if you are increasing the input, the light output also increased. So you need to draw a graph for forward bias diode with voltage and current. If you draw a graph for this by taking voltage on this and current on this, current is milliamperes, voltage in volts, you will get a graph something like this, most similar to your forward bias diode. Okay, and choose two different points, find the slope, from the slope calculate the resistance of the LED in forward bias by finding the slope as delta I in milliamperes, convert this into amperes by delta V. So if I take 1 by slope, I'll get resistance R. Now I am doing an experiment for LED in reverse bias. First switch it off and you need to change the diode. Here the diode is in forward bias. If you use this, the same diode, same LED is connected, but for reverse bias you need to change this TP6 to TP7, and it is now measuring the current through the reverse bias LED. So in reverse bias the current is very low and the supplied current in reverse bias is not sufficient to give any light out of the LED. So LED must be operated in forward bias. Hence LED is a luminescent device which emits light when it is under forward bias. Now I am explaining how to take readings for reverse bias. Now reverse bias current is small, therefore keep this knob in 2 microamperes. If there is a power range, you can switch over to 20 microamperes. Now I am keeping it. And I am keeping this in 20 volts. And after making the connection, switch on the power. Okay. So if I switch on the power, initially I am getting 0 0. So I note down in the tabular form for the reverse bias as starting voltage 0 in volts and the current is 0 in microamperes. Now I change the input voltage to 0.5. Directly, if you want to take one reading at 0.15, you can take. So I am taking it as 0.15 and I write current in microamperes as 0, almost 0. So I will be taking 0 only. Then I increase the voltage to, okay, 0.5. Directly I will go to 0.5. So I am going to 0.5 and I note down the respective current in the reverse bias. So it is 0.52 and I'll write it as 0.52 and the corresponding value is, say it is almost 0 or 0.002. Okay. Now I change the value. So now I will adjust the current to 1 volt because previously we have taken value at 0.52. Now I go and check and adjust the input voltage or say voltage across the diode as 1. Okay, it is 1. Okay, and you see the current is still 0 almost. So I'll put 1 volt and I write 0 only. This is also making 0. I'll write 0 only. Then I'll go for 2 volts directly. Okay, I'll change this 2 volts and see I'm increased this value in forward bias 2 volts, but current is almost 0. Okay, and there is no light coming out of the LED. This LED we have used, but there is no light. In reverse bias, it will not function and to emit a light. Now I'll go to 3 volts. Okay. So I'm now moving to 3 volts. So this 3 volts, the current is still 0, and I note down this value as 3, almost 3, and 0 current. And I go on increasing to 4. But you can see from the board that the diode is not giving out any light. Okay. So no light is emitted in reverse bias by the, okay. So there is no light coming out of it. So applied is 4, voltage across the diode is 4, but the current is almost 0. Okay, then I go for 5, and still the current is 0, and thereby there is no light also in the reverse bias LED. Likewise, I'll take readings for 5, 6. Also I'll say 6 volts, and 6 volts also current is 0. I'm increasing, and I stop here for, okay, 6 volts, the current is 0. I keep it 0, and there is no light coming out of this one. Therefore, in reverse bias, there is no light coming out of the diode LED. So these are the readings. Therefore, if you draw a graph, you have already drawn graph for forward bias taking voltage and current on y-axis, and this graph is similar to the forward bias. But here in this case, almost 0, whatever the voltage. So I'll get a line just like this because there is no current. These are the IV characteristics of a LED. So in this experiment, you need to find out slope in the linear region, find the forward biased resistance. Okay, as 1 by slope is equal to 1 by slope. You know, slope is delta I by delta V, 1 by slope is this. Convert I, this milliamperes into amperes, we will get the value. And the same experiment you are also going to do in a virtual lab by using Tinkercad. So you also compare the values you got from the Tinkercad lab, virtual lab, and also from our demonstration video. Thank you. I stop here.